Hi class, in this part of Chapter 17 we want to talk about low mass stars. Those are stars that have masses less than 2 times the mass of the Sun, and talk about how they end their lives. They live on the main sequence for a long time, and then some things are changing, and then what are these changes that occur that then end up having the ultimate kind of demise of the star remaining? What's the last thing that will be left over after the star dies? So how do low mass stars die? So here's the main sequence diagram, or the HR diagram that we've seen before, and the main sequence again is a kind of a fuzzy-ish line that runs in this diagonal direction, and these are all stars that are burning hydrogen in their core, and so they're converting hydrogen into helium, and as they do that, there are some gradual changes that occur, and so this is a fuzzy band of stars. A star doesn't just sit in one position on this diagram its whole life. Its luminosity and its temperature do gradually change over time. But bigger changes are ahead once the hydrogen starts to become depleted in the core. So a star is on the main sequence as long as it's burning hydrogen into helium in its core. And during this time, there's this sort of equilibrium between gravity squeezing inward and energy sort of pressure pushing outward. And there's a nice balance. If somehow gravity was to squeeze a little harder to increase the temperature of the core, the reaction rates, the nuclear fusion rates would increase, and that increased energy production would push outward harder, causing the core then to expand, and then this expansion would actually cause the core to cool, and then the reaction rates would go back down again. So there's this sort of balance, this back and forth balance between gravity and energy production that keeps the star fairly stable. But ultimately, there are some changes. Ultimately, we're losing some particles. We'll talk about how these changes are occurring as a star becomes kind of goes off the main sequence. So if we look inside of the stars, and we'll look at high mass stars in more detail later, but if we look inside of stars, we've talked about the Sun and how the Sun has a layer of convection near the surface, and has what we call a radiation zone in the deeper interior. And the idea is that we want to think about how energy is transported from the interior, from the core, to the exterior of the star, to the photosphere. And energy can move around in various ways. One is by what's called radiation, where just the light is basically just traveling as light, and it's kind of bouncing off of charged particles as it goes. And that's what we call radiative transport. So in the interior of the Sun, it's so hot that all we have is a plasma of particles and electrons, protons, electrons, and the light has a very hard time getting through there. It doesn't get absorbed by these particles, it just bounces off of them. So it takes a very long time for light to travel from the core outward to these further out regions here. And so, but light is still traveling as light. It's bouncing off of particles. It's not getting absorbed. The temperature is just too high for these particles to form any kind of atoms that could then absorb energy. Once the temperature gets a little bit cooler up in this region for our Sun, then that light energy can actually get absorbed and cause the atoms and particles that are there to actually, absorb that energy, turn it into energy of motion, kinetic energy. And so the gases below actually get hot, they get warmer, they rise to the top, and they release their energy when they get to the top. They cool off and they sink back down. And so you've got this convection zone here. And it turns out that the lower the mass star is, the deeper this convection zone is, because the temperatures overall are cooler. And so the idea then is that we have convection when it's cooler, we have radiation when it's hotter, and so the coolest stars are entirely convective. Everything inside of the star is getting mixed up. Gases are just constantly being churned and mixed and so on. Our Sun is sort of in between. It's very hot in the interior, so it's radiative, but then as you get closer to the outside, it becomes convective because the temperatures are cooler. And so if you think about the really massive stars that are actually really hot everywhere, they have no convective zone at all on the exterior. The gas is so hot that the light is leaving the star entirely as just pure light, bouncing off of particles as it goes. It never actually gets absorbed, causing the gases to then rise and churn like a convecting pot of boiling water, for example. But what's interesting is that in the very interior of a very, very massive star, it is so incredibly hot there that radiation alone isn't enough for that energy to escape. There's also convection going on in the very high interior, a very hot interior. So it's kind of strange. It's not entirely correct to say that convection happens when it's cooler and radiation is transported as radiative transport when it's hotter. If it's really, really hot, then you actually do get some convection in there, because there's no way that radiation alone can transport that energy fast enough. So we'll talk about high mass stars in more detail later. But this is stuff we've mentioned before. I just wanted to review it a little bit. So what's happening then in the core of these main sequence stars, these low mass main sequence stars, and really any of them, any main sequence star, is that we're having a decrease in the number of particles in the core, because we're taking 4 hydrogen nuclei, protons, and converting them into 1 helium nucleus. We often call that an alpha particle. We're losing particles. The number of particles in the core is decreasing. And so pressure, the outward pressure of this core, depends on 2 things. It depends on the temperature, and it depends on the number of particles. And so we're losing the number of particles. And that allows the pressure, that makes the pressure go down, which allows gravity to contract the core even more. And that actually causes then a gradual increase in temperature of the core. So even when the star is on the main sequence, the temperature of the core is gradually increasing, and therefore the reaction rate, fusion reaction rate, is gradually increasing. And so the energy production is gradually increasing. The luminosity is gradually increasing. This is true for any star on the main sequence. So then what happens if a star runs out of its hydrogen in the core? It just has a bunch of helium there. What happens? Does it just start cooling off? Does it shrink and heat up? Does it expand and heat up? Does it start fusing helium immediately? What actually happens? Well, if you run out of hydrogen in the core, that energy production is reduced, and gravity can start squeezing even harder. Gravity squeezing means that the core is going to shrink, and when the core shrinks, when gravity squeezes something and makes it shrink, it's going to heat up. And so the core is definitely going to shrink and heat up. The temperature isn't yet great enough for helium nuclei to come together to form something else. It takes a much higher temperature for helium to produce something else. So if we look at star clusters, observing star clusters is really important, because we can see a bunch of stars that were all born at about the same time, and we can see some patterns. And we do see, in fact, that there's a main sequence, and there are stars that are starting to die, and we see some stars in different places on the main sequence. So here's, for example, the sun. As it lives its life, still burning hydrogen in the core, we would see its luminosity gradually increasing, its temperature rate remaining roughly the same, but its luminosity gradually increasing. And then in star clusters, we see the dying stars as well, the stars that are not on the main sequence, and we see them off to the right of the main sequence. And so there's a particular path that stars travel, in a sense, on the main sequence, and we kind of trace that out. And when we look at the HR diagram of an entire cluster of stars, and so it looks like from these observations that stars become cooler and redder. Cooler and redder is kind of redundant, but they become cooler and more luminous. So they become red and brighter as they die. So we want to understand what's going on there. How is that happening? So again, as the core contracts, hydrogen begins fusing into helium then, or once hydrogen is fusing into helium and you've got just this inert helium core, that core gets squeezed, gravity causes it to get hotter, but now it gets hot enough around the exterior of the core for there to be a shell of hydrogen that starts burning into helium. And so there's some gas around the core that was just sitting there before, and as the core is shrinking, so does this shell of gas around it. It shrinks as well. As it shrinks, it heats up too. And as it heats up, then it might get to a temperature where it can start converting hydrogen into helium. And so there's nothing in the core then to push against gravity. Gravity is going to continue to shrink this thing, even though we start producing energy in this shell. We start to produce extra energy in this shell. That extra energy is not enough to stop this core from shrinking and heating up. It'll continue to shrink and heat up. So we've got what we call like a broken thermostat in the star. Normally, again, if the core that's producing energy starts to shrink and heat up, the reaction rate would increase, causing the core to expand. But there is no reaction rate right now in this core, in the very center. There's nothing going on. So gravity just keeps squeezing it, getting it hotter and hotter and hotter, and that causes the shell of material around it to burn hydrogen even faster and faster and faster. And so we have an increased production of energy in the core while it's shrinking. That increased production in energy actually causes the outer layers of the star to expand. that extra energy pushes the outer layers outward, the whole star becomes brighter. And also because of this expansion, the energy is being emitted, given off over a much bigger area. The star actually looks cooler on the outside. So it seems sort of backwards, but it isn't. The calculations, the models show this clearly, and the observations in star clusters is clear as well, in that as the star expands, it becomes brighter and it becomes cooler on the surface. So it's a much bigger surface area that it can emit this energy from. And so it emits a lot of energy because it's got a big surface area, even though it might be a little cooler than it was before. So the core is shrinking while the outer layers are expanding. We'll continue to see this sort of opposite thing going on between the outer layers and the core of the star, and how they're opposite. Helium fusion doesn't begin right away because the temperature has to get to a certain point. And so gradually the temperature is going to rise. Eventually it's going to get up to 100 million Kelvin. Once it does that, then we can start taking these helium nuclei and squeezing them together to form carbon. And this happens in a particular process. It's called the triple alpha process. There are some stars, if they're very small, if they're very little stars, very low mass stars, the temperature just will never get high enough for those stars to burn helium into carbon. The temperature again has to be very high because we've got 2 protons in these nuclei, and they're positively charged. They don't want to be near these 2 protons and these other nuclei. And so you have to squeeze them together even harder, and you do that by making them hit each other at a much higher speed. And a higher speed corresponds to higher temperature. So the temperatures have to be high enough for nuclear fusion to occur with helium. And there are some stars where the temperature will just never get hot enough, and they will end up just as a core of helium, inert helium, just doing nothing. And eventually the outer layers of that object, that star, would just kind of get blown away, and you'll be left with what we call a helium white dwarf, a very, very hot core of helium supported by what's called degeneracy pressure. Eventually it'll just cool off and cool off and cool off. It'll just be a solid ball of helium. Very, very dense, extremely dense. Call that a helium white dwarf. We don't have any helium white dwarfs yet in the universe because any star that would do this would live for much longer than the age of the universe so far. So as far as we can tell, and nobody's ever discovered one, there shouldn't be any helium white dwarfs yet in the universe. There will be other ones though. There are other white dwarfs that come from bigger stars that have already died. So what happens in a low mass star then when the core temperature rises enough for helium fusion to actually begin? Does it start slowly? Does the hydrogen fusion just stop? Does helium fusion rise sharply? So what happens? Helium fusion is going to start eventually for stars that are massive enough, but how does it start? So the key here is that there's this thing called degeneracy pressure in the stars, and in the cores actually. And that is a pressure that is quantum mechanical. It's something that we can only explain with quantum mechanics, and we've talked about this previously. But it's a situation where the thermal pressure in the core is not supporting, it's not pushing against gravity enough to support the core, but rather it's this degeneracy pressure. So as we change the thermal pressure, as we change the temperature, we may not get the same kind of expansion that we would expect of the core in a normal core, where degeneracy pressure is not a factor. So what happens is ultimately the helium fusion is going to actually start very quickly. So why is that? So if we think again about this thermostat of a low mass star, as this star is expanding into a red giant, the outer layers are getting bigger because the core is shrinking. There's this broken thermostat. All right, so the core is shrinking. Normally, if the core shrinks, then the reaction rate speeds up, and that produces more energy, causing the core then to expand. But that's not happening in this red giant that is expanding because of this shrinking core in the center. So we've got the shrinking core in the center with a hydrogen burning shell around it, producing a lot of energy, causing the star to become very big. Degeneracy pressure then ultimately is what keeps the core from shrinking further. And the temperature then in the core can actually gradually increase because there's this hydrogen fusion that's happening outside the core, and it's depositing more inert helium into the core. So the number of particles is increasing, the temperature could be increasing, but the outward pressure is not changing because we've got this degeneracy pressure thing supporting the core against gravity. But once the core does get hot enough, around 100 million, helium fusion can start. When helium fusion starts, there's going to be a new production of energy. You're going to get some extra energy that's produced in the core. And the extra energy is going to heat up the core. Normally, if the core got heated up, it would expand. But it's degeneracy pressure right now that's pushing against gravity. So it takes a little bit of time for the thermal energy to get strong enough to actually push against gravity. And so the temperature can actually increase very rapidly. The temperature would increase slowly if the core was able to expand while the temperature increased. The temperature could increase slowly in that case. But in this case, the temperature increases rapidly because it's almost like there's enough space, in a sense, for the temperature to increase, because degeneracy pressure is kind of supporting the outer surface of the core. So the energy can be produced, the temperature can increase very rapidly. Eventually, the thermal pressure is enough to start pushing against gravity, and eventually the core does start to expand. But the helium fusion process begins as a burst. It's like we call it the helium flash. It's a huge increase in production of energy for just a brief moment. And eventually the core starts to expand, and then it cools, and then the temperature starts to become more in equilibrium. So finally the thermostat is fixed. This thermostat idea now is okay again. So the core is being supported by thermal pressure now. It pushes outward against gravity. If the reaction rate were to somehow increase a little bit now, as we're burning helium into carbon, then that extra energy would cause the core to expand. That would actually cause the core to cool. Gravity would then be able to squeeze it a little bit, make it a little smaller, and so on. There'd be a nice balance. So once a star is burning helium in the core, there is a balance now to everything. And so the star is now another kind of a more stable object. Not as maybe as stable as it was before as a hydrogen burning star, but still pretty stable. So if we look at the life track now at this point, so the star as it comes off the main sequence, it changes a little bit, and it starts burning hydrogen in a shell around an inert core. That extra energy production, the shrinking core, causes the outer layers to expand. That extra energy production pushes the outer layers out so they actually cool, so the star becomes more red, and also the luminosity increases because of that extra energy production. Eventually we get to a point where the temperature is so high that helium fusion can begin, but it begins in a flash. There's a rapid increase in temperature because of that support of the core by degeneracy pressure. But once the core starts to expand because of the increase in thermal pressure, the expanding core starts to make the star actually decrease in luminosity. This is a little bit weird, but what happens is that now you're back in equilibrium again, or you're close to it at least, and the expanding core actually cools. And so all the reactions decrease. The reaction rate goes down. So the core expands. And this includes the shell of hydrogen around the core. That reaction rate goes down too. So the reaction rate overall goes down. The amount of energy production goes down. The luminosity therefore goes down. As the luminosity goes down, gravity can squeeze the outer layers as well and kind of squeeze the whole star again and make it smaller. A star getting smaller is actually going to look warmer on the outside. And so the star warms up, it moves a little bit to the left, and it moves downward because the luminosity decreases. And then there are a bunch of stars. You could find a bunch of stars on this, what we call the horizontal branch. These stars here would be stars that are happily burning helium in the core. And so they're fairly stable now once again. And they're helium burning red giants, definitely larger than they were on the main sequence. And maybe they could be the same temperature as they were on the main sequence. It just depends on some other factors. When the star is a red giant, it swells up and sometimes it can lose mass. Mass can be kind of blown off of its surface. And so exactly where it kind of ends up along these horizontal branches depends on how much mass it has lost when it was a red giant. And so now we have a star that's happily burning helium in its core, but it also has a hydrogen shell burning hydrogen into helium around that core. So this is what it looks like. We've got helium core fusion in here. We've got hydrogen fusion around the core in a shell. But now it's a stable star for a little while at least, not for very long, but for a little while. So the star doesn't shrink or expand anymore at this point. There are gradual changes though, because as helium is converted into carbon, again we're losing numbers of particles in here, and gradually the core is shrinking. But it's gradual. It's much more gradual than it was before, because there's a lot of energy being produced in this in the core here. So looking at a cluster again, these are actual experimental observations of a cluster. You can see there's a bunch of X's here. This is this thing called the horizontal branch. These would represent a bunch of stars burning helium in their core. This is the turn-off point. This indicates stars that are just starting to die. So this is how you would determine the age of the cluster, by looking at the kind of the star that's just about to die. How old would that normally be? How long would that normally live? That would be the age of your cluster. You've got your subgiants, which are stars that are just about to start. They're kind of like running out of hydrogen in the core. They're just about to turn into red giants. The red giants are these stars over here that don't have helium burning in the core yet, but they have the hydrogen burning in a shell. And then these would be stars that are just about to do their helium flash. And then the stars that have done the helium flash would move on over here, and they'd start converting helium. I mean, they come down this way pretty quickly. They start quickly converting helium into hydrogen or into carbon in the core and become a horizontal branch star. So what happens after that? What happens after the stars have a nice helium burning core with a shell of hydrogen around it? Well, eventually the outermost layers of the star are going to be kind of blown away into this thing called a planetary nebula. So let's look at how that happens. So when the star's core runs out of helium now, what happens? Does it explode? Does carbon fusion begin right away? Does the core cool off, or does helium fuse in a shell around the core? It's just like it happened for hydrogen. When hydrogen fusion stopped in the core shrunk, everything heated up, and because of the increased temperature, the shell of gas around the core could then start doing something. And in this case, the shell is going to start burning helium into carbon in a shell around the core. So after the core helium stops, the core helium fusion stops, helium is fusing then in a core, or in a shell, converting helium into carbon in this shell. That carbon is being deposited into the core, but hydrogen fusion is also continuing in a shell around this helium shell. So there's a lot of sources of energy production, and this inert carbon core is shrinking, and now everything's out of balance again. The star is going to start to swell. The core is going to shrink. That shrinking core is going to heat up. This double shell burning is going to increase rapidly. There's going to be a lot more energy produced in the core, and that extra energy is going to push the outer layers outward even more than they were pushed outward before. So the star is going to expand to an even greater size than it was before, a much larger red giant than it was before. And it turns out that this stage is very sort of chaotic. There's not much balance there. So what we see are these thermal pulses. There's these sort of pulses in energy production as the energy is produced in the core, and these pulses make the star kind of expand and then contract a little bit, and then expand and contract a little bit. And you've also got convection possibly in the star that's kind of like dredging up carbon from the core and kind of bringing it to the surface. And during these expansions, some material gets blown away from the star, and this carbon then that was created in the core gets kind of blown out into space. And so we have these stars that are like populating the universe with carbon, which is good because we're all made of carbon. This is where our carbon came from, was from these stars. So the double shell burning ends finally with a pulse that is so big, so violent. It's not like an explosion that happens with the massive stars, but it's a pretty big pulse that ultimately sheds the outer layers of the star into space. And what you're left with in the end, what's left behind is just the core of the star, a carbon core, which is again a white dwarf, but it's a carbon white dwarf in this case. The carbon, the temperature inside the core never got hot enough to burn carbon. So for a star that's 2 solar masses or less, the temperature will never get high enough to burn carbon into something. You'll be left with a carbon white dwarf, maybe with some helium and hydrogen on top of it that's still fusing, but eventually it'll be just pure carbon with no nuclear fusion happening at all. ultimately in the end. And that white dwarf will eventually cool off, but it'll take a very long time. So the fusion process stops. About 600 million Kelvin is what you need to burn carbon into something else. It's possible that during this process there is some helium that could fuse to carbon to create something like oxygen. But you're not going to get two carbons coming together to form something. There's just not enough energy there. There's not enough collision energy to make those things stick together, to make them get close enough to stick together. And ultimately then degeneracy pressure again is what supports this carbon ball against gravity. So a white dwarf that's produced might be about the size of the Earth, and it'll stay that size. Gravity isn't going to squeeze it anymore. It's going to be really, really hot initially, so it looks white hot. Eventually, though, over billions and billions of years, it'll cool off and become, maybe black. You might call it a black dwarf. Eventually, it'll be, just a very cool ball of carbon, like a diamond in space. So here's kind of a picture of all these little steps in the process for a star like our sun. It gradually leaves the main sequence. It becomes a subgiant and then a red giant as the inert helium core is shrinking. The outer layers are expanding. Then there's the helium flash. Right after the helium flash, the star becomes somewhat stable again, burning helium in the core. But that doesn't last very long. Once helium in the core is depleted, the core starts shrinking again. And now you have two layers of fusion going on, helium and hydrogen fusion, causing a lot more energy to be produced, much higher luminosities, much larger outer atmosphere, outer layers of the star, much bigger red giant than you had before. And then you've got these pulses that are taking the outer layers and kind of puffing them outward. Eventually, one last big puff pushes the outer layers completely away, and you're left behind with this white dwarf that gradually, it's very, very hot. Eventually, it reaches like a maximum temperature once all the fusion is finished, and then it gradually cools off. But it takes billions of years for that to happen. So, in terms of what might happen to the Earth, well, this is the star, our sun, right now, and this is a graph of the brightness, the luminosity, and the time. So right now, our sun's about 5 billion years old, and gradually, while it's on the main sequence, gradually it's going to increase in luminosity. Gradually. Eventually, it's going to leave the main sequence and become a red giant and increase luminosity pretty quickly, and also increase size. We'll look at that too. But these processes in the later stages of the star are going to happen fairly quickly. Look at how the time scale is changing. So after about 10 billion years, the star is going to start to die. But after about 12 billion years total, we'll be done. So the last few stages of the star take only 1.5 billion years or so, compared to the lifetime on the main sequence of about 10 billion years. So the luminosity is going to go up to a really high value when the helium flash occurs. The star is going to be very bright. The luminosity is going to go back down again, and while you're burning helium fairly stably in the core, the luminosity is pretty stable for a little while. But then once helium runs out in the core, the luminosity is going to go back up again as the core shrinks. And then you're going to have these pulses of thermal pulses where the luminosity goes up and down, up and down, up and down. And then finally the outer layers are puffed away, and you're left with a white dwarf that just gets dimmer and dimmer and dimmer and dimmer and dimmer. And then in terms of the size of the sun, again, this looks very similar to the last graph, but so luminosity and size are very much related to each other. The sun is a certain size, just call it 1. Gradually, once the sun leaves the main sequence, it's going to become, eventually, once it reaches the helium flash, it's going to be over 100 times as big as it was right now. And so that's going to be pretty big. The sun is going to be just about at the Earth's orbit. And so imagine the surface of the sun, like right next to the Earth. Temperatures on the Earth are going to get really, really hot. Life is going to be just unable to survive. Maybe there'll be some microorganisms that can survive, but certainly not human life. But then eventually, when the helium flash happens, luminosity is going to go down. The core is going to expand. The star is going to shrink. It'll be burning helium nice and stably in its core, but it'll be bigger than it was before. Not as big as it'll be bigger than it was right now, but not as big as it was at the helium flash. And then eventually you're going to have these thermal pulses that make the star expand and contract, and so on. And then you'll become a white dwarf that is very, very small, about the size of the Earth. And it'll stay that size for eternity. So that's everything we need to know about this section in Chapter 17. So basically just that we have hydrogen fusion in the core, that's a main sequence star. We then get hydrogen fusion in a shell around a contracting core, that's when we turn into a red giant. And then finally, if we get helium fusion in the core, if the star is massive enough, then we go into what's called the horizontal branch on the HR diagram. But then once that helium fusion ends in the core shrinks again, and you've got this double shell burning of hydrogen and helium, and you become a red giant again. It's a bigger red giant than you had before, and the star swells and swells and eventually puffs off its outer layers, leaving behind an inert carbon white dwarf.